Welcome to everyone to this Clojure meetup from the Zürich Clojure user group. Before we start, I just want to tell you who are our sponsors for tonight. So first we have Zoltán Kinyó, who is generous to offer us the beer for everyone who is present here. And otherwise there is Codesmith, who provides the location and tonight the speaker. And there is 200 OK that take care of the meetup group. Thank you to everyone. Also, if you were if you are listening live earlier, you heard some beats, and this was by a good friend of mine that I would name Birdsong tonight. So before we start, the subject today is about GraalVM and Clojure. But before we start, I just want to give you a link to show you a link to a blog post by JetBrains, because I think it might interest you. What is really cool, so JetBrains is, maybe you know it, if you program a lot in Java, you certainly know IntelliJ and maybe you use it. And JetBrains is actually creating a whole new editor called Fleet. Exactly what it is not so important here, but they are presenting how, in a series of blog posts, how they are building it. And now they are in this third part of this series of blog posts explaining how this new editor is built. There is state management. So how do they manage the state in the editor? And if you read the article, and look at the pictures, sometimes you come at this picture, and this picture we know all very well, right? It's this so-called epochal time model that Richiki showed many times. You have a pure state, you have transition to a new state and things. And actually, if you read the article, you will see that they are really very much inspired by this talk, and they even link the talk and talk about Richiki himself. And then later when you read, they explain how they store their data. It will be maybe in memory, part on disk. And you see things like that. That reminds us very clearly to Datomic. And they actually say this is Datoms and Datomic. And so it's actually great to see that all those ideas that Richiki pushed for all these years with Clojure are adopted in other contexts, like the creation of a new editor by JetBrains. So I thought that was cool. So now let's go back to the subject of today, which is about GraalVM and Clojure. And let me go here. So what is GraalVM, right? So GraalVM is basically a new just-in-time compiler for the GVM, for OpenJDK. And so the GVM works like this, that in order to work really fast as it does nowadays, the bytecode is not interpreted all the time. With time, it gets analyzed by the just-in-time compiler, and then it gets translated into machine code so that it runs really natively. And the whole GVM and the whole OpenJDK GVM, and in particular the just-in-time compiler, they are written in C++. It's a very old project. And GraalVM is a new just-in-time compiler, so it's not a completely new VM, but it's written in Java. So they do the same. They take bytecode and transform it to native code. And the reason why a lot of people are interested into this is that it's able to do this even ahead of time and produce native image executables. So right now, the old just-in-time compiler written in C++ just run within the context of the GVM. So if you want to take advantage of it, you take advantage of it without even noticing. You have to install the GVM, and you have to start the GVM like you normally do. And with GraalVM, you can do the same, but you can also do ahead of time compilation where all this transformation that normally happens at runtime for the GVM happens at compile time, and then you get a binary executable. And before we continue, we need to talk a bit about compilation, because there are a lot of different kind of compilations that we're talking about. So I just prepare so that so that nobody is confused if when I say compiler, maybe sometimes I don't always fully qualify. So we will have two kind of compilers here in this little presentation. The first is the Clojure compiler that takes Clojure code and compiles it to GVM bytecode. And this happens mainly at two different moments. First, it happens at runtime. Every time you evaluate Clojure code, ever you load, you say load file, and then the compiler will execute form by form and will compile it to bytecode, load it on the GVM, and then execute the code which has been generated. And you use it also at the REPL all the time. Every time you send an expression to the REPL, you are actually using the Clojure compiler that compiles this to GVM bytecode and then execute it. And there is another context where you can do that, which is called the also ahead of time compilation. And the idea is that instead of at runtime, instead of loading the Clojure code, compiling it to GVM bytecode and running the GVM bytecode, is to do this compilation to GVM bytecode in advance. And then you just have a bunch of class files, which are like if they would have been generated by the Java compiler. And then the GVM can load those much faster than running the Clojure compiler to produce this bytecode. So this is the first kind of compilation that we will talk about. And the second is what I already mentioned earlier, is GVM bytecode to, let's call it machine code. And this is done by the Hotspot just-in-time compiler and also newly by the GraalVM. And again, there are two contexts, right? There are this runtime context, which is the GVM is running, there is bytecode running, it's getting interpreted, it's getting profiled, and then the just-in-time compiler decide now it's time to compile this little part in native code, and then it's run instead of the bytecode. And for GraalVM, of course, there is again the same idea that you can do ahead of time compilation to transform the bytecode into the native image. So you can see, in order to have a Clojure program which is a native image, we will have to do the two compilation. First, compile ahead of time Clojure to have Java bytecode, and then ahead of time compile the Java bytecode to the machine code via the GraalVM infrastructure tooling. So I hope it's clear for everyone that there are these two compilation and what purpose they need. So GraalVM, because as we know, the Java virtual machine is a very dynamic environment. You can load classes, you can unload them, you can do all these things. And the GraalVM native image tool, there is a kind of very reduced runtime environment called the Substrate VM, which has not all these dynamic capabilities of the GVM. In particular, it cannot create new classes. So as you can imagine, every time that if I have, this means that the tool must know all the classes in advance. This is the first thing. And second thing is there is very limited reflection support. And actually you have to know in advance all the reflective code that you will make so that the machine can, the compilation can bake this in, right? So this is a second big restriction. And for Clojure, it means in particular that you can not use facilities like eval. You can also not use the Clojure compiler itself. Because this involves creating classes. Every time you evaluate a function declaration or a lambda, you are actually creating a new class that gets loaded on the GVM. So, of course, you can no more do that in the native image, in the program that you want to compile to a native image. And we saw already this problem last time where we met, when we talked about Babashka, which is this tool to quickly see Clojure environment to do scripting and stuff like that. He wanted to, so the creator, Michel Borkelt, wanted to have this tool that starts very quickly and that that can execute Clojure code, and of course you cannot use the Clojure compiler if you combine it with the GraalVM, so he created his own little interpreter for Clojure, for a subset of Clojure, to avoid this problem. So why would you want to compile to native code? Well, there are to a native object, and there are mainly, I would say, two reasons for that. The first one is that because all the classes must be are known in advance, and there is no more this dynamic loading, and everything is compiled down to machine code, it starts much faster than a normal Java program. And this is the main selling point. And the second, I would say, for little utilities like Babashka and other what-time utilities that you would like to use on your command line, it allows you to distribute the program without having to ship a GVM or to expect that the user of your tool has a GVM available on their system, because it's a self-contained executable like you would obtain if you would compile Go or C++ or whatever other language that compiles to machine code directly. And so how do we do this in Clojure? Well, actually there is a fantastic tool, fantastic document and tooling which have been compiled by those people, and that explains in detail everything how to do it. And so we will now do this with a small example program that I created, and see where it brings us. Is there questions up to now? No, great. So here we are. So let's. So when I thought, what kind of little tool, what kind of tool could I do to present where it would make sense? And I thought, well, very often people complain about Clojure startup time in, let's say, in a server environment when you do little one-shot jobs, right? And it starts, it takes a long time to start, and if it's a server that runs for a long time, maybe you don't care that much. But if it's just a one-shot function that would run on an Amazon Lambda function, then you would like it to start fast. So I thought, let's do a little program that is just a one-shot thing that runs a little report from the database, so reads record from the database and then export an XML file. Right? It would be like kind of a task that you run daily, kind of report. Right? So so what do we have? I have to start. I think I have to start. Yeah. Now comes the demo effect. Yeah, of course, I have to maybe load. So I'm just starting a REPL and a database in memory. And what we have are two tables. A table called record that has, two properties. It's random, and there are children to these records, which are sub-records, which are the primary keys, record ID and sec, and have some more properties. And what we want is to generate an XML file with those. And the XML file should look something like this, right, where we have a list of records, and then maybe we want the two first property there, but sub-record, we don't want the sec, we just want them in the correct order, and maybe we want to do some little transformation on the data. So that's what we want to do. And so the tables are empty, so let's fill them with some test data, with some 1,000. And did it work? Yes, it did. So now I should have on the console, here I should have some data in it. So yeah, as you can see, and sub-record is here also with data. It's not so important what is inside the data. And since we want to actually produce for every record, we want the records and the property and the list of sub-records. How do we fetch this efficiently from the database? And we have a Postgres database, and actually the easiest way is to use the JSON facilities of the Postgres database to fetch JSON documents that represent a whole record with the sub-records. So the JSON, the query looks like this. I have record, I join on the sub-record using the record ID key, and I want to extract the ID, the properties, and then from the sub-records I want the 3 properties in their correct order. And so if I execute this, you will see that I have all these documents here. Perfect. And let's say we're not happy about this, so our employer that wants this XML file wants also a substitution for this letter, which are in property 1. And we have a file here in we have a kind of mapping file that will map this in. So this is our task. So how do we do this in Clojure? Very quickly. How do we do this? So we have this query object. We will read from the query. We will read the records via an open cursor from the database. And then we have some function to do actually the mapping. So if I have such thing with these 3 keys and I have these statuses, this code file, then this is a way that I can produce a sub-segment of an XML file, right? Using this vector notation that we know from Hiccup, for instance, and also from the XML libraries in Clojure. And the same for if we have a record, then we can map stuff. And at the end, the only thing that we have to do is actually create. We use transducers, so there is a very, very cool facilities from a JDBC library called Plan, which just open a cursor, which is a reducible thing. So I want to reduce, and then I want to write in a XML file. I want to write all this record and transform them accordingly. Right. This sounds a bit complicated, but it's really only that.
You're not even using any XML libraries.
I use the library, the XML library from Clojure, which is using this X3, XEmit, and stuff like that. So it's using the lazy variant of the XML so that I can generate the file. And of course, the file could be very big. I don't want to have it all in memory, so I'm streaming all of that into the file. Is it clear what we're doing? Yeah.
So you're building a report tool from
Yeah.
the database?
Yeah.
And some configuration file in JSON?
Yes.
That spits out some XML.
Yes, that's it.
And
Right.
you do the SQL in like JSON style?
No, the SQL is just here. I made it easy to read, so I don't use other libraries. I just write the SQL like that. I don't know if I don't know.
Some JSON, the database is in a normal relation.
It's a Postgres database, right? It's a normal Postgres database running now in the background. So here, if I go here, I have this Postgres database. I have this record that I actually populated earlier, and here I have sub-records for them. It's random generation of stuff.
And instead of getting rows, you get some JSON.
And here, well, the point is I want to read all these sub records for one record, and I want to stream all of that because maybe I have 100,000 of them, right? I don't want to load them all in memory. And so the easiest is to pack the sub records with the record itself. And to do that, you could use arrays or maybe SQL arrays to do that, but it's actually the easiest way is to use JSON. So actually we read a JSON. At the end, we have a list of JSON documents that we transform into XML, right? But we stream them from the database, where there is a cursor, we open them, we load 10,000 records at a time, and we write them immediately. It gets all flushed, and therefore you need very little memory, even if you have a very big report. But I don't want to lose so much more time on that part of the program. We can talk about this later if you're interested. But it's just I needed an example of something that you would maybe do in your job, right, you will need to write this kind of transformation.
And at this point of time, you don't know if it will be compatible with GraalVM.
It is actually. I don't use any dynamic stuff. I just use normal Clojure. Yes, but I don't know at the time. Yes, indeed. You have to pay attention. But as long as you don't use eval and you don't use library that use eval, you're kind of safe. So now, how can we execute this code? Right? We have this main function, this namespace with a main function, and so if we want to execute the code, we can actually use the Clojure tooling for that. Just as an example, so I have to give two files. The first is this mapping file for these definitions that makes kind of no sense, but it's not so important. And then I want to produce one file with that. As you can see, it starts and then it produces the file. So if I lint it and open it, it's not the same as earlier because I just regenerated with other data, but it's generated the file, right? And now it was quite fast, but the point is let's try to compile. Let's try to compile it and let's see what happens. So what I did when using the Clojure tool, CLG tool, I just really start the Clojure main runtime, and then it loads my my namespace with the Clojure file and compile this in memory, compile this to bytecode, and then load it and then execute it. And now the first step to have a native object is to do actually the, let me delete all of this, is actually to do the compilation itself, the ahead of time compilation of Clojure from Clojure code to Java bytecode. And for this, I have here a little namespace, and I use the compile Clojure function from the tools build API that Clojure provides. So it's a library that helps you if you want yourself to program to write little program that compiles to Clojure, then you can use this API to do that. And that's exactly what we do here. So here I say please compile the code, and the code gets compiled. And then here you see, if I refresh this, I have now a bunch of classes, and you can see here I have, no, let's get back to my program. So it's in Cosmic. So let's go see that. And you can see here I have, for my main namespace, I have different classes. These are all functions that are present in the file, because every function in Clojure corresponds to a class, right? So you can see this has all been compiled. And also very important to notice is that this compilation is recursive. So all the Clojure code that I would ever load, even from other libraries like JSONista or Camel Snake Kebab, that gets compiled as well, because everything has to be compiled recursively. So now I could actually start this with the Java command, but of course I need to provide the class path for all my libraries and where the class is. And actually I have here exactly that. So let's just duplicate this for the moment and have a look at this. So as you can see, it's really big. It's on one line, unfortunately, but it's okay. And this is actually calling with the Java, calling my class with a normal Java executable. And with the class path, it contains every library, inclusive the classes I have compiled. Right, so let's just execute that for fun. And then it gets exported. Right now I have a file. It's not important to look at it, but I have a file test2 which is the same export that I just did, but this time using compiled Clojure code that has been compiled to GVM. And now I would like to do the last step, which I would like to have a native object. And for this I need 2 steps. The first one is I need to gather, as I say earlier, there is a limitation with reflection, so you need to gather all the reflection calls that you will ever make. And the question is, well, how do you know which reflection call you make? And nowadays there is an agent that allows you to collect this information. So you just start your program normally as you would, but you add this Java agent to the executable, and this agent will actually gather all the reflective code, put them in a file that you can use in the later process. So let's just do that. And you can see here, the only thing I do is I call Java, I call with the class path. This is the whole stuff that you saw earlier, but it's just a call of via the build tool API. And then I just call this, and it's really normal Java. But the very important thing is that I actually use this agent that will instrument the GVM to collect this. Yes?
So what if you don't run part of your program that has a reflective code?
I think then you will enter into trouble. Because it means that at the moment where you want to do that, the call will not work because you won't have declared.
So it collects runtime, that's right? So it collects runtime information.
Yes, exactly. Yes, it collects runtime information. That's why you call Java, and then it instruments the GVM via the agent mechanism, right? And then, I mean, this is the same mechanism that is used for debuggers or for profilers to measure stuff. And then it will generate this file. So just let's have a look. And now, if we look at that, it's actually called my program. Now it's really fast because I have few data, but it has really called my program, run my program, and then analyzed which calls, reflective calls are made. And here, I have here, it has generated this file, which is all the reflective calls. So for instance, from this class, we actually will call this method via reflection. And so the tool should bake this in so that the reflection call succeeds. So that's actually, you don't have a lot of things to do, but you have to make sure that everything gets run through. And now when this is done, we can actually use the tool to compile with the native image tool. It's a tool which is provided by GraalVM, and you give the class path, you give and then you give the namespace that will be starting, and then with this reflection config, it will actually construct the native executable. So it takes some time. So before I answer a question, I start the process, and now it's starting, and you can see it's starting, so you can see the time it takes. Yes?
I have a question to this reflection call. So because sometimes I do set going on reflections in order to eliminate any reflection calls.
You should do that.
Also a possibility?
Yes, that's what you should actually do. Thank you for mentioning that. It's actually here. You need to do that, yes. Because you otherwise you will have trouble when you run the. And so you can see it's actually compiling now to native code. So it takes, no, it's done. And we should have now in the target folder, we should have this data processing file, which is an executable. So I can actually call it. It needs no VM. It's really an object that you would have even if you would have compile, like you would have with Go or C++ or C compilation. And so I did some comparison between how fast it is and what's happening when you run stuff. And I show you first, we can do a little bit of experiments ourselves. I just want to show you a table that actually tells us a bit the story. So also what is important to know that GraalVM, as I told you, is a just-in-time compiler like the normal hotspot just-in-time compiler. So you can run GraalVM with a normal Java executable. So when you download GraalVM, you get actually a Java environment where GraalVM is installed as just-in-time compiler, and it will run like any normal Java program, just using a different just-in-time compiler. And so I just did some experiments where I have in my database 1,000, 10,000, 50,000, 100,000 rows that I want to export, right? So the more rows, the longer it takes. And the first number is the real time that it takes. It's averaged. And the second is the user time, right? Because if you have multiprocessor, you can have bigger user time, because it means that in the first example, we had 1 second to export these 1,000 rows, but it took 2.5 user time seconds. It means there were many threads active at the same time, right? So that's why you get more, you use more than just the real time. And what is interesting to see is that at the beginning, when you just have 1,000 rows, when you start with the GVM, it takes 1 second, and if you use a native tool, it's instantaneous, so it takes 150 milliseconds. But as you add rows, as you export more rows, you can see that the advantage shrinks, and even it becomes worse with time. And so I ask myself why. I don't know exactly, but I think that the GVM is actually extremely good at doing just-in-time compilation, and my program is so small that 1 second, 1.5 seconds is enough to optimize it. And the point is the just-in-time compiler, they have runtime statistics to help them deciding how to optimally generate native code. And the native tooling does not have that. It has to do kind of generic machine code. And you can see with time it performs less well. And so I think maybe my example was not so good after all, because it's the startup is so small. I mean, if I were in Java in a Spring context, I don't load this all Spring things that, or in Clojure, a whole set of a big and complicated system that takes so much time to load, and then you would see a really more radical difference. I think also you would see a greater difference if you were on a machine with a single processor. I tried, unfortunately I had not the time to do it. I wanted to try with, Amazon has now some IRM, the Graviton 2 processors, and they have a virtual machine with just one CPU, right? And so here you can, using multiple threads, I imagine that the just-in-time compiler, gather statistic on another thread and prepare the stuff on another thread. And maybe if you don't have that, then the whole optimization takes actually more time if you just have one thread in the system available. But you can see that quite quickly for simple stuff, the just-in-time compiler is actually really, really good. And actually, I did not show, last time I tried, I did not do it again, but there is a flag to disable the just-in-time compiler. You need to force interpreting bytecode, and it's really slow. It takes like for 1,000 rows, it takes like 30 seconds or something like that. So you really, really see that the just-in-time compiler very quickly is able to optimize to generate efficient native code. So where do we want to use? Where do you want to use GraalVM? I guess for me the facet is more you have really to test if it brings really something to you, both for short tasks and long tasks, because it may not always. And then you have also to think about other aspects like there are other aspects like then startup time. There is also packaging of your artifacts. For instance, if you use a normal GVM, well, then if you use Docker, for instance, let's say, then you can really layer. You have many layers on your Docker image, right? You have your GVM, and then maybe you have all your dependencies, and then you just have your Clojure compiled code. And if your dependency does not change all the time, then every new release is just a little bit of disk space. And the native tool is just one big executable, like if you would do an Uber jar, right? It's even more than an Uber jar because it's all the jars plus the runtime, everything compiled. And you can see here, the difference, right? This is 60 mega for the data processing native image, and it's like 5 mega for the classes themselves. So this is also maybe an aspect that you want to think about.
Did you also measure the memory usage?
No, I did not. I know it's very difficult because it's a native. I did a little bit, but what I know is that it needs more memory. So typically you need more memory with the native tooling than with the Java runtime. Don't ask me why, I don't know. And so I think also if you need more memory anyway, for instance, say we want to run in a Lambda function, I mean, this is a really small example and I allocate 64 megabytes of RAM. I just wanted to make sure that it streams the stuff. It cannot have all the XML file in memory. But also on AWS Lambda, for instance, the more memory you allocate, the more CPU power you get. So I'm sure that, as we saw earlier, that the normal Java needs a bit more CPU at the beginning, probably to do all this statistic and do the just-in-time compiler, but then it will become irrelevant if you need to use a big AWS Lambda with a bigger size, because you will get CPU power anyway. Oh, is something I have to mention. GraalVM has 2 releases, and here I just use the community version. So the community version is restricted. I will just tell you about what. And there is an enterprise version, which is more advanced, and but it costs, all right. You have to pay for every server, so it's not completely for free. To Oracle. And so what are the restrictions of the enterprise or the normal, or what has the enterprise edition more? So the enterprise edition has 2 things more. First, it has more GC options. If you have the community version, you just have the serial GC as an option. You don't have the G1 or other kind of GC at disposal. And with the enterprise version, I think you get the G1 or the Z compile, one of both. And the other thing is that the enterprise edition, the just-in-time compiler, has more feature to better support, even better just-in-time compiling, and it has also yet another agent to collect runtime statistics to produce better native code, right? So as I told you earlier, here I think, I'm not sure. I did not check, of course. I don't know enough. But here we can see. I suppose that the GVM gets faster because it has access to runtime statistics to better inline, to better compile to native code. What the native tool does not have. I mean, it just has the class file. And there is a thing called advanced profiling, which is available only with the enterprise edition, that allows you to profile in advance, to make to analyze in advance to produce better native images. And so it would mean that you would get the best of both worlds, right? You would have the advanced profiling, so the real good profiling of the runtime to produce good just-in-time code, but it's in advance, and so you have very fast startup times. And they have, of course, a lot of success stories about that. You can find them on their webpage. Yeah. So it's kind of complicated to set up, I must say. So I think you do it really when you have a reason. Either you want this fast startup, or you want like distribute these kind of small tools to other people, like Babashka does, and it's a pure executable that you can that starts fast and that it's really very handy on the command line, right? Because on the command line, you want things that starts immediately and not have 1 or 2 second startup time. And generally, you do small tasks, so you don't care if the runtime is less ideal than on the pure GVM.
Can you do GUI?
No, you cannot. I think, as far as I'm aware, the what's the name? AVT is not supported. AWT is not supported. So, which is the basic for. So maybe there are some graphics libraries that can be attached, but I don't think. So you don't have swing, for instance.
Mm-hmm.
That's a good question, yeah. So you cannot do.
That would be a use case, right?
Yes, yes.
Native applications.
I don't think it's possible yet. Last time I checked
Maybe
it.
low-level graphics and with some custom.
Yeah, I don't know. Maybe people will. I don't know how. Also, there are possibilities to interact with native code like Java can do, right? GNI and stuff like that, and there are also possibilities there. So I guess you could, but I guess the difficulty with AWT is that it's supposed to be multi-platform and stuff like that. Or maybe it's I'm mistaken. I think it's available experimentally on Linux only, and not on every platform. But you would have to check. So, but they are definitely working on that.
So if you do a native image, can you compile it as a library so you can invoke it from C?
But that's this I don't know. This I don't know. But I don't know if you can create a library object or a dynamic library object, or if it has to be, an executable. I don't know. I guess it has to be an executable.
Is the executable OS declared?
Yes, and this is also, I guess, for people maintaining projects in different operating system. I guess it's a pain because the tool is not cross-compiling. So if you want to generate a Windows executable, you have to run the tool on Windows. If you want to generate a Mac executable, you have to run a tool, if I'm not mistaken. Yeah. And so even more respect for Babashka and other tools like that takes all of this into account. But it's so GraalVM is actually also much more than that. They have a full framework called the Truffle framework to implement other languages on top of it without having to compile to Java bytecode. So there is a lot of activities around GraalVM. But yeah. So I don't know if you have any more question. If not, then thank you for attending. I will close also the stream now, and let's have a beer here and let's continue the discussion. Thank you. Bye bye.